Hey there, my name is Alejandro and welcome back for day 50 of me doing the NeetCode 150 challenge. So today we're doing our very last LeetCode medium binary search problem. And of course, without further ado, let's get straight into it. Okay, today we get a LeetCode medium problem 981, time-based key value store. Design a time-based key value data structure that can store multiple values for the same key, okay, at different timestamps and retrieve the key's value at a certain timestamp. Okay, what does this mean? Implement the timestamp class. Oh, this is going to be one of those design questions. Okay, time map initializes the object of the data structure. Okay, set. Okay, string key, string value, and timestamp. Stores the key with the value at the given timestamp. String get, string key and timestamp returns a value such that set was called previously with timestamp prev is less than or equal to timestamp. If there are multiple such values, it returns the value associated with the largest timestamp prev. If there are no values, return empty array. Wait, okay. String key and timestamp returns a value such that set was called previously with timestamp prev is less than or equal to timestamp. Okay, sure. Okay. If there are multiple such values, it returns the value associated with the largest timestamp ref. Interesting. So it's like almost like we want to have a list sorted based on timestamps. And okay, I don't want to implement like an AVL tree. I really, at some point, I needed to learn how to use, the sorted list in Python, right? And just like, assume that I use something like an AVL tree under the hood. Okay. So we set things with a key and value and a timestamp. Here, get with a key and timestamp. Return a value such that set was called. Wait, so we're given a key, first of all. That's interesting. Value such that set was called previously with timestamp prev is less than or equal to timestamp. Multiple such values, it returns the value associated with the largest time. Okay, I don't get it. Okay, let's look at an example. Time map. Here we set with the value foo bar 1, get foo 1. This is interesting. It's almost as if we don't care at all about the values, right? We can have them as tuples. Get gives me bar. So inside key foo there's bar, and yeah, there's timestamp less or equal to 1. I'm having trouble, right? How is this binary search and not like, sorted list, right? Or like using an AVL tree or using like a BSD? Because the point is that we essentially need to do like insertion sorts, right? We need a sorted array. Okay, no hints for this problem in case we need them. Okay. Ooh. Oh no. Timestamp is up to 10 to the 7. Other timestamps set are strictly increasing. The set and get. Well, why is it a new timestamp, right? Will it not always be a greater timestamp? Oh. Wait, okay, no. This is easier. This timestamp is always bigger, right? There is no insertion sorts. It's always appending to the end of the array. Wait, okay, this is not a difficult binary search question then. It is binary search, but it's even easier than the previous few that we've been doing, no? Wait, no, it's not even binary search. Set, yeah. Wait. Yeah, this set was larger. Is there any other examples? All the timestamp of set are strictly increasing. Okay. Oh, it's just that when you get a get query, you might. Okay. I understand where there's gonna be binary search. Okay. This is actually super straightforward, right? This is gonna be. We're just gonna have a self.d is equal to a dictionary. So these are gonna be key to array mappings. And okay, this is actually going to be super straightforward. Right, so here is going to be set is going to be self.d of key. If key not in self.d of key is equal to an array with just, you know, value. Actually, we'll just say self.d of key is equal to an empty array. And now here we'll say self.key.append, you know, a tuple with timestamp and value, right? Or we can do value and timestamp, right? But the point is that we need to make sure that we have the right values, right? So value timestamp to make our life easy. Here will be a 0 and a 1, right? So here our array will be, you know, equals self.d of key. Assert length of self.d.get, you know, key and an empty array is greater than 0. Okay, so we'll just have that assert for now. Array is equal to self.d of key, right? Okay, so the timestamps are strictly increasing as they get called. Okay, they just give us to us as timestamp instead of us setting one. Okay, what? Okay, all good. It's just that now we don't have to do insertion sorts because we keep adding those timestamps in you know, increasing order, so that's very good, right? And so now we essentially have, you know, increasing order timestamps. So it's like, you know, timestamp, it's like, oh, is this timestamp you know, greater or equal to a current timestamp? So it'll be true for a lot of them and then false at some point, right? So this is just typical, you know, leftmost, rightmost binary search here, where it's like there's a bunch of trues and then falses. We want to find the rightmost occurrence of a true in this case, right? The biggest timestamp such that that timestamp is still less than or equal to this one, right? That's essentially it. So essentially in this array, it's like we'll do L comma R is equal to 0, comma length of R minus 1, and then here we'll say, you know, while L less than or equal to R, here we'll even have a result. We want what, right? So we'll just do none, right? Is there guaranteed to always be a solution? You know, assert res is not none, and then here return res or something, right? So here we'll do while L is less than or equal to R. Per timestamp. We want the largest one, right? So 0. Curval. R of 0. Maybe here we do 1, right? Mid is equal to L plus R over 2. We'll say, hey, if best timestamp, if val comma timestamp is equal to R of mid. If yeah, R of mid at timestamp is less than or equal to timestamp, then we'll say, okay, this is a valid case, right? Valid case. So first check if it's better, right? If val comma time is equal to R of mid. If time, or cur val, cur timestamp. Cur timestamp is less than or equal to timestamp. Now here, update current best result if needed. So here we'll say, you know, if cur timestamp is greater than best timestamp, and here we'll say, you know, best timestamp is equal to cur timestamp, and here we'll say best val is equal to cur val, right? And then just in case, now it's like, okay, we have found a valid case, right? We have found a valid true. There might be more trues to the right of me, right? So in that case, I just do L is equal to mid plus 1, right? Otherwise, this huge else clause, it's like, okay, we have not found a valid timestamp, right? This means that this timestamp is too large. So we need to look in the left subhalf to find even smaller ones, right? So that makes a lot of sense. Here return best value, right? Okay. Okay, so let's run this. Okay, so this is accepted. Let's submit. Here we get a wrong answer. Okay. Love high 10. Love low 10. 20. Get love 5. The first one might not actually be a valid result, right? Okay, I'm done. Best val. Okay. So here we'll do 0. Right, so I want to make sure that this triggers the very first time. So I want this to be better than the current timestamp, right? So here we'll say is equal to none and float of negative infinity, right? And here we'll just do assert best val is not none, right? So let's just do this. My Hadood, okay. Oh, is an empty string in those cases, right? Okay. Okay, so there we go. Submit. And okay. Oh yeah, we don't need this anymore. And we don't even need this. Okay. Okay, there we go. Self.d.get key, comma, an empty array. There we go. There we go. Okay, there we go. Okay. There we go. Bada bing, bada boom. Okay, we finally have a working solution. So that is absolutely wonderful. Okay, so that took a little bit of time, but now we have a good working solution. And it seems like we're at the bit of the bottom of the standard deviation here. Okay, using a hash map is very, very smart. Right, if key is not in self.d, okay. Can we get away with just that? No, we probably can't. We probably can't. I mean, we might as well try, but yeah, we probably we can't. Okay. You know, it's fine. Okay, we're at 23% and so on, but I don't see how, you know, you can do a better solution than this in terms of asymptotic complexity. Okay. Maybe it's just it takes a couple retries of just resubmitting and so on. Now we get 51%. Maybe we resubmit, we get here, and so on, blah blah blah. Okay, but this is a standard deviation, so this is good. Okay, so as always, in all my videos, I do a quick recap of how I was able to solve the problem. So essentially here, it's like, okay, we want, the thing to realize is whenever you set with a timestamp here, this is always bigger than any other timestamp you would have done for this key beforehand, right? So essentially you can keep a sorted array by timestamp by always adding things to the end, right? So essentially to init, I keep track of a dictionary, right? Because we have keys, and then for each key, we have, you know, an array of values and the corresponding timestamps, right? So here it's like, I initialize, you know, self.d as a dictionary. D for literally dictionary. Then in my set function, it's like, okay, we have a key, a value, and a timestamp, right? I want to essentially add, you know, for each key, I have, you know, an array of values and timestamp tuples, right? So here, when I want to set, you know, a value and timestamp for a certain key, I go search up for the array and the key. key is not inside of my dictionary, then I initialize it to an empty array, right? Otherwise, it's already an existing array. In that case, it's like, okay, I know that this timestamp is larger than any other timestamp inside of that that array over here. So in that case, I just add it to the end with a tuple, with the first value being the value here that's passed in, and the second one being the timestamp, right? So I keep them as tuple pairs. That way I keep track of both the value and timestamp of every single element whenever I call a set function, right? Otherwise, here for the get function, all that we do is like, okay, let's get, you know, the array at key inside of our dictionary, right? And here I just, as default value, I do an empty array in case that key does not exist inside the dictionary. Then I know in like the default case, if there are no, you know, valid timestamp, blah, 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 the default case that I need to return is an empty string. I know that just because I went inside of this case and I saw like, hey, here there's, you know, inside of the love key, there's both a high at value 10 and a low at value 20. Here, when I try to get, you know, love at 5, there's no timestamp that's less than or equal to 5, right? Because 10 and 20 are both bigger than 5. And so here it says, oh, return an empty string. So I initialize this to an empty string and like, you know, an unreasonable timestamp that is smaller than any other possible timestamp at the beginning. And then here I just do a typical binary search, right? So all I do is like, you know, set my left and right, so you know the left and right indices of my array that I'm currently looking at. And then it's like, okay, typical binary search. And then I look, okay, is this current element that I'm looking at the middle between left and right a valid one, right? Is it the case that, you know, the timestamp pref here, right, which I actually call my current timestamp, is less than or equal to the timestamp that's passed into this function? If so, then this is a valid case, right? So I update my best results seen so far. If the current timestamp that I'm looking at is bigger than the best timestamp, right? Because we want the largest timestamp pref such that this condition is true, right? So if this condition is true and it's happens to be that the current timestamp is better than the best one we've seen so far, then we update the best one that we've seen so far to the current timestamp, and obviously, you know, update its corresponding value as well, because this is the value that corresponds to this current timestamp, which happens to be the best one, right? Otherwise, it remains unchanged as the best value, right? And then in that case, it's like, okay, we have seen a valid case that technically works, right? And so now there might be other timestamps that are even larger than current timestamp that are also valid, right? So here in that case, we want to search in the right subhalf of our array. Otherwise, if current timestamp was actually bigger than timestamp, then that means that like, hey, this was an invalid timestamp, and every other timestamp to the right of me is even bigger than this one, which will also therefore be bigger than timestamp. So we want to ignore everything that's on the right hand side. So in the else clause, we say, okay, I'll limit myself to only searching in the left subhalf, right? Where it's like I essentially have a list of, you know, a value in timestamp tuples that are sorted in increasing order by timestamp, right? So essentially that's why I'm doing binary search on that. And then whenever I find, you know, a valid case, I update my best result in those cases, right? And then at the very end, I return best val, which will be, you know, the corresponding value to the timestamp with largest value that still meets this criteria over here. And that's essentially how I was able to solve the problem. But as always, you know what? Let's make sure that we check the fact that we did this problem. And this is a very special one, not only because it is the last LeetCode medium binary search problem, but this officially completes 50 out of the 150 NeetCode 150 problems. We're officially 1/3 of the way there, which feels absolutely fantastic. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. And otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.